So in the last class we were looking at the negative feedback system. So I'll draw this model again. So last class we discussed what happens if the amplifier here has a frequency dependent gain, that is it has, let us say, one pole. So we assume that the transfer function of the forward amplifier is of this form: A0 by 1 plus S by P1. So what is the loop gain in this case? Sorry? Yeah, it is beta times the same transfer function, beta times A0 by 1 plus S by P1. So we decided, if we plot the, let's say, the magnitude of this function alone, let's say versus omega, I am plotting the magnitude. Let us say this is magnitude of L. At low frequencies it starts with beta A0, and after it encounters the first pole, so it drops with the slope, something like this will drop. So here, what is the closed loop gain H of S in terms of the loop gain? Let me make some more space. Yeah, can you tell me what is H of S in terms of L of S? Yeah, H infinity times loop gain by 1 plus loop gain, and in this case H infinity is exactly 1 by beta. So this times L of S by 1 plus L of S, right? And remember that, let's say there is no pole here, the pole is at infinity. What would be the ideal closed loop gain you will have from the system? If the pole is not present at all, what would have been the ideal closed loop gain? 1 by beta times? Yeah, approximately it's 1 by beta, but the exact value, remember, is 1 by beta times A0 beta by 1 plus A0 beta, right? So let's say it's approximately starting the closed loop gain. Let's say it starts with 1 by beta. Now I know for a fact this is not going to be the same value throughout the frequency, because as you see from this expression, as long as the magnitude of the loop gain is much greater than 1, this can be approximated to be 1 and you get 1 by beta. So this marks an important point, and remember this is all in log scale, so this is, although it is 0 dB, right? This frequency is what we designated as omega u loop. That is the frequency at which the magnitude of the loop gain drops to unity. And what is that frequency? What is the expression for this frequency? Yeah, you can, doesn't take a lot of time to find it also. Again, calculation is pretty straightforward. This is the loop gain, and I know for a fact that the unity loop gain frequency is going to be much greater than my first pole, because the gain is very large and the gain is starting to drop only after encountering this point. So by the time it drops to unity, this frequency will be much greater than P1. So for frequencies much greater than P1, how can I approximate the denominator as S by P1? So you just have beta A0 by S by P1. You take this, equate the magnitude to 1, that straight away gives you the unity loop gain frequency. Okay. So you know for a fact, for very low frequencies, the gain is going to be 1 by beta, or maybe I'll draw it. 1 by beta can be slightly smaller than this. So let's say this is 1 by beta. And for very large frequencies, the magnitude of the loop gain is much smaller than 1. Then we argued that it is as though the feedback itself is not present, because whatever is happening here, an extremely small fraction of that is what is feedback. So you can as though say that there is no feedback. So the closed loop transfer function at high frequencies, what is it approximately? A of S. So if I sketch A of S, that is going to be a scaled version of the same plot. Right, this is A of S, so this is A0. Okay. So let's say I quickly do that, something like this. Okay. So at very high frequencies, it is going to basically follow this plot, something like this. And in the last class we computed what was the closed loop pole. What was the closed loop pole location? Sorry? Yeah, omega u loop. It's the same as the unity loop gain frequency. And what was the 3 dB bandwidth for the closed loop system? It is the same. For a first order system, the pole location is indeed the 3 dB bandwidth, right? So, I mean, you can get this also graphically, right? Because I know for low frequencies, it is going to follow this line. At very high frequencies, it is going to follow this line. And I know in closed loop, how many poles I'll have? One pole. So, I'll join this, and wherever it intersects is my corner frequency. And if I had drawn it correctly, this should have intersected at omega u loop. If it's not matching, like how you plot graphs, I'll make it cross here. It should cross here. Good. So this is something you should remember. For a first order system which does not contain any zeros, the unity loop gain frequency is exactly equal to the closed loop pole, which is indeed the closed loop 3 dB bandwidth also. Okay. So we stopped at this point in the last class. Let's resume. Again, let me take this. Let me write the results once again. The transfer function I have assumed is a0 upon 1 plus s by p1. And if the feedback factor is beta, what was the unity loop gain frequency? What is the unity loop gain frequency? Beta a0 p1. Okay. And this was in turn equal to my 3 dB bandwidth for the closed loop system as well as the closed loop pole location also. Fine. Great. So now let us say at the input of this closed loop system, right, the input is here, V in, I apply a unit step. Okay. This is V in. And let us say the amplifier has no pole. What will happen to the output? How will it look like? If I say this is V out, how will V out look like? If there is no pole in the system, how will V out look like? It's constant. I mean, the input is having a step jump like this. So how will the output look like? It will also, I mean, if the input is, let us say, jumping up from 0 to 1, what will happen to the output? It will jump from 0 to, okay, what will be the value to which it will reach? A into beta, what? A times this, no. This is a closed loop system. I'm feeding in a step input of 1 volt, let us say. What will be the value to which it will reach? Yeah, 1 by beta times A naught beta. Fine. Okay. And of course, the ideal value you wanted was basically, let us say this, I'll draw that separately. This ideal value is 1 by beta, right? You wanted 1 by beta as the final gain, but due to the finite DC gain, you end up with this. So this is the scenario if there is no pole. Now I know that my amplifier has one pole. So how will the output behave? Rise exponentially. Why? I mean, it's a first order system. So natural response of a first order system is an exponential behavior. So it will essentially do this. Okay. So let's say I call this value to be some V out or V naught F, final value of the output. Can you give me a closed form expression for V out of t, assuming this to be t equal to 0? How can you write V out of t? I mean, look at, I mean, what is the initial voltage for V out here? 0. What is the final voltage? Yeah, I mean, let's say it's V naught F. Now tell me what is the exponential, equation? 1 minus t by tau and into V naught. What should come exactly? V naught? Yeah, V naught, the final voltage, which I have denoted as V naught F. Is that fine? And what is tau in this system? Sorry? 1 by P1. Okay. Why 1 by P1? For first order system? He's saying time constant should be equal to the reciprocal of what? 3 dB frequency. What is the 3 dB frequency of the system? Yeah, what is the, you're also saying the same thing, but what is the pole location in the system? Omega U loop, what is that? Yeah, remember we are looking at open loop response or the closed loop response. So this is a first order system, and the pole location, you guys were absolutely right. This is the, I'll say closed loop pole. I'll say pole closed loop, whatever. So that's basically 1 by beta n naught times. Okay. That's basically 1 by omega U loop. I'll write it directly. Is okay? And hopefully everyone is familiar with writing, first order systems, like step response and stuff. Great. So the bottom line, so if I have a negative feedback loop and the forward amplifier has one pole like this is the settling behavior you will have. So at the end of the day, for this negative feedback loop, you will be given some specifications. And of course, one main specification is H infinity. Now your job is to find out what parameter of the open loop or the loop gain will help us get the required specification. So here, what will H infinity tell us? What decides H infinity? Beta, right? In this case, it is 1 by beta, but otherwise it will be 1 by beta times something. But it is the feedback factor that determines the ideal closed loop gain you want. So if this H infinity is given, that gives you what is the feedback factor you should put in this. Now of course, you can also be specified as to till what frequency you want the ideal closed loop gain, and that frequency is what? Yeah, basically that's a 3 dB bandwidth for the closed loop system, right? So you can have a specification saying I have my closed loop gain should be H infinity till so much frequency. That's indirectly saying 3 dB bandwidth or the time constant, right? Either of them. And as you guys pointed, this gives us the unity loop gain frequency for the loop gain. And omega U loop, what does it, what is the expression for omega U loop in our case? Beta A naught times P1. And of course, I know what is what is beta. So, now the only thing is A naught P1 is design choice. So, you can choose anything for A naught, anything for P1, if these are the only two specs. But in practice, what can be another specification of the closed loop system that can help you find what value of A naught you should use? That is, okay, let me rephrase the same. So, is there some specification you can define for the closed loop system that will help you determine what is the open loop gain I can use? Amplification is just the gain, right? 1 by beta. Closed loop? That's basically beta A naught P1. That is not setting anything on A naught. I know what is the product, but individually for A naught I don't know anything, right? What is loop gain? That's what this is, right? I don't know. Beta into? I'm asking, So can you specify some specification for the closed loop system that will help me fix the gain A0, DC gain A0? What error are we talking about? Yeah, what is it? So remember that if I had infinite A0, what would have changed in this response? It will reach the, ideally it would have reached this value, right? Now if the gain is finite, you have a small error. And what is this error now? What is the difference between the two? If I take the difference between this and this, what do I get? 1 by? Okay. So this is a steady state error. So if I give you the steady state error, from there you can actually find what is the gain value issue, right? I mean, in fact, let us say in practice I give you some op amp, okay, and I say that this can have a gain, let us say as high as 1 million. So, how will you measure this gain in practice? Or let us say you design an op amp, you know that let us say you design for a gain of that can be as high as so much, 10 power 6. So, how do you think you will finally measure and verify that it is indeed having this gain? Great, if you apply an input, so let us say supply voltage is 1 volts. What will the input you apply? 10 power minus? That's 0.1 microvolt, right? And you think that's practically, doable thing? I mean, even if you generate it, there is going to be a lot of noise that is going to completely mask this signal out. So how do you think we'll measure? How do you think we'll measure? Exactly, right? See, think of it like this. We are trying to measure the gain of this. And why did I have to have such a large gain? To be used in negative feedback. So it should make sense that I can only measure it in negative feedback. One simple thing is put it like this. Give a step here. I give an example. So the output will basically, let's say, settle like this. You find what is the steady state error and you do. That's how we measure it. Otherwise, you can't do anything. Okay? Anyways. Cool. So now we know if our amplifier has one pole and if I put the amplifier in negative feedback, what's going to happen? The only issue is that this is going to take some time to settle, and the settling speed indeed depends on the unity loop gain frequency. Is that clear? Great. So now we have done with the first order case. So let's move on to what happens if the amplifier has two poles. So let's say A of S is A0 by, I have two poles, S by P1 into 1 plus S by P2, and if the feedback factor is beta, my loop gain is going to be beta times this. So let me also write it for completeness. Loop gain is beta times A0 by 1 plus S by P1 times 1 plus S by P2. And once again, what is the closed loop gain H of S in terms of L of S? Yeah, H infinity into this. So L of S by 1 plus L of S. Okay. And in this case, I know what H infinity is. I'll write it directly. It's 1 by P2. Okay. So let's try to do the same exercise we did before. So let's try to sketch the loop gain. So let's say I plot it here. is the magnitude. So it's going to start with what value? At DC, what is the value? Beta I naught. And let us say the first pole is somewhere here. Randomly choosing something. What will be the slope once it encounters one pole? Minus 20 dB per decade. So I'll just say 20 dB per decade. And let's say at this point it encounters the second pole. What will be the slope after it hits the second pole? Great. 20 times 2 is 40. Everyone remembers 20 tables. So it does something like this. I will not try the slope. It's too much. Okay. Great. So if I similarly sketch the face, then maybe, or it's okay. I'll not sketch the face for now, or I can sketch it. Let's say sketch it. If I sketch the face, so what is the value with which the face will start? 0. And where to what value will it reach asymptotically? Minus 180. 2 poles, so you get with minus 180 something. I am just roughly drawing it, not drawn for scale. Okay, minus 180. So maybe I'll not draw maybe I can draw it. Let it become small. It's okay, it'll be there. Yeah. Cool. So as usual, let's try to plot the closed loop transfer function now. And again, for very low frequencies, what would be the closed loop gain? At DC, what is the closed loop gain? Yeah, that approximately 1 by beta. So let me just put it approximately 1 by beta. And the same thing holds good, right? As long as the loop gain's magnitude is much greater than 1, it's going to follow this. So let's say I draw. And for frequencies for which the loop gain's magnitude is much smaller than 1, maybe I'll draw it slightly more like this. So for frequencies where the magnitude is much smaller than 1, what will happen to the closed loop gain? Okay. The feedback is not there, so the closed loop gain is A of s, right? So the A of s is essentially a scaled version of the same plot. So I'll draw with dotted lines like this, something, right? So just for quick thing, so high frequencies, it's going to do this much I know. Now when I had the first order case, things were trivial. I just had one pole, so I could just do this, wherever it intersects, the plot is done. But here in closed loop, how many poles I'll have? 2 poles. So without knowing the relative positions of the closed loop poles, I can't sketch what's going to happen in between, right? So there is no other thing. Let's do the calculation. So I'll write h of s. I'll rewrite it like this: 1 by beta times 1 by 1 plus 1 by L of s. That will just bring out the s terms here, so that you don't have to do LCM business. If I do this, I'll get 1 by what do I get? 1 plus s by p1 to 1 plus s by p2 by a naught beta. So again, you can now take LCM. So a naught beta goes in the numerator and denominator. Okay. So let me move it to next page. Or I'll write it separately. H of s is 1 by beta times a naught beta by, what do I have? Yeah, a naught beta plus, okay. Now, I mean, remember that the standard second order transfer function format is some k naught by 1 plus s by omega n times the quality factor plus s square by omega n square, right? Or, I mean, okay, alternate thing is to write in terms of the damping factor. So 1 plus 2, sorry, 1 plus 2, whatever, this is the symbol, right? 2 zeta, omega, sorry, s by omega n. Okay. This is the standard form. So, can you expand this and tell me what is the values for each of them? But first of all, without doing calculations, what do you think K naught is equal to? K naught is the closed loop gain at DC. What is the closed loop gain at DC? That's approximately, exactly what is it? 1 by beta times? A naught beta? Again, it's the same thing, right? If I cancel beta, it's A by 1 plus A beta, same thing. So this is something you should know straight away. Now for the rest of the two, can you calculate and tell me what do you get for the natural frequency and the damping factor? Or it's okay, let's not spend time on that. It's algebra. Let me do quickly. I think this should be approximately root of A naught beta times P1 P2, right? If I take this, and this should be, I think, beta. I think should get something like this. If someone did it quickly, tell me if it's correct. Otherwise, let's assume this is correct and move on. I think should get something like this. Yeah, makes sense to me. Let's wait for a minute. If someone does it, check if it's correct. Else, we'll assume it is correct and move on. Yeah, it's about that. Okay, this is correct, so you can trust me. If this is incorrect, we'll get to know later, but as of now, I think it's correct. Okay, let's move on. So let me actually copy paste this. So again, just to remind you, we are looking at the closed loop system. Okay, and I find that the damping factor is this. Let me also write the transfer function we are looking at. This is the closed loop transfer function. Cool. So now tell me, what are the possible cases I can have for the damping factor? I'm sure everyone has done this. Huh? Fine. So what are the three cases I can have for this damping factor? Yeah, okay. So one is less than 1. And what is that called? Underdamped. Let's say it's equal to 1. What is it called? Critically damped. And if it's greater than 1, overdamped. Great. Why do you classify it this way? I mean, why don't I look at damping factor greater than 10, equal to 10, less than 10? Why only 1? Because the textbook said so. or like let us say is okay. Why do you even classify it like this? What does it say for the closed loop system? Let me not even come to stability, right? I'm just looking at, my pursuit was the following, right? We wanted to sketch the closed loop transfer function. Let's rewind back. This is what I want to fill in the blanks here. I said that without knowing the closed loop pole locations, I cannot do, and that's why I did this. So instead of, I found the closed loop transfer function, and then I'm looking at the damping factor. Why? I'm not looking at output, right? I'm looking at the poles. Okay, let's say calculate the closed loop poles here, right? So can you tell me if I look at closed loop poles, it's a quadratic equation, right? Second order quadratic equation. What is the formula? Minus b plus or minus whatever. Yeah. Okay. So tell me what is the location now? What is minus b? Here what is the b term? Minus 2 zeta by omega n plus or minus square root of 4 zeta square by omega n square minus 4 by omega n square by 2 by omega n square. Okay. So let's quickly do this. So if I do this, I get minus zeta omega n plus or minus omega n square, you get omega n into square root of So now if I look at the discriminant here, I have this square root of this zeta square minus 1. So now we can clearly see, right? This could be real or imaginary. So that's why we do this. So let us say if zeta is equal to 1, what can you say about the closed loop poles? Real, but what about the location? Some more information can you give me? They are both equal. That's the important thing, right? So let me mark the closed loop poles as P1 hat and P2 hat. Okay. If it's critically damped, I know that they are going to be lying on top of each other exactly. And what will be that location? Yeah, that's correct. But from here, what is the final location of the pole? Zeta omega n, but zeta is what value? What is the value then? Okay, I'll just write it as omega n. Assume that it is all left half plane is assumed. Okay. Just to avoid confusion, remember that here when I write P1 hat, P2 hat, they are the closed loop pole locations. Okay. Now in the damping factor expression, I have P1, P2. What are they? Poles of the loop gain or the open loop gain. Okay. So this is the forward amplifier's poles. This is the closed loop system's pole. Okay. So please don't get confused. So this is for critically damped. So let us say I look at over damped. If zeta is greater than 1, do you think the poles are real or imaginary or complex? Real. And that's why we look at this case. Okay. It's not randomly we choose it. And what can you say about the locations? Or will they be will they be equal or they'll be different? They will be apart, but they will be real. And let us say, okay, let's write the pole location. So it's going to be this one. And the lowest frequency pole, do you think it will be smaller than omega n or greater than omega n? Why greater than omega n? The question is, I know that in this case, I have two poles on the real axis. This is going to be a real number, no questions. But the question I am asking is, if I look at the lowest frequency pole, there are two poles. One is at a lower frequency. The lower frequency pole, do you think its location is less than omega n or greater than omega n? Is that fine? Because, take some number. Let's say I took zeta as 2. What do I get? I have 2 omega n plus or minus omega n into root 3. So this is minus 2 omega n plus 1.7, what is 3, right? 2 omega n minus, so what is the lower frequency here? 2 minus 1.73, that's smaller than omega n, right? So that is the point I want to make. Let us say P1 hat is the lower frequency pole. P1 hat will be smaller than omega n. And also I know P1 hat and P2 hat They are real numbers. So that's the point I want to make, that if it's overdamped, the lower frequency pole will be actually smaller than the pole you will have for critically damped case. Cool. And what about this case? If it's underdamped, my zeta is less than 1. So this will become real or imaginary? We'll have complex conjugate poles. So my pole locations will be of the form sigma naught plus or minus some j omega naught. Okay. And also for this case, I have sigma naught and omega naught. So this is the real part, this is the imaginary part. Again, the magnitude of sigma naught, do you think it is greater than omega n or smaller than omega n? Real part sigma naught is just zeta omega n. My zeta is less than 1, that is smaller. What about the imaginary part? Zeta is less than 1. So I mean, if I write it like other way, it's j omega n into square root of 1 minus zeta square, right? So zeta is less than 1. So do you think this thing will be less than 1 or greater than 1? Both of them will be less than omega naught. Okay. Is clear? This is the point you should remember. Okay, cool. Yes. So now we have information about the closed loop pole. So again, so just to rewind back, our goal was to sketch the closed loop transfer function. That is, closed loop frequency response, not the transfer function. And when I do that, I just intuitively know what can happen at very low frequencies and very high frequencies. To do things in between, I'll have to know the location of closed loop poles. That's why I calculated the transfer function. And I say I can have 3 different cases. So let's try to see what will happen in the 3 cases, and then we can make some comments. Just erase this part, not needed. Yeah, let me just plot the magnitude alone. This is omega. This is the magnitude of the closed loop gain, right? So one thing I already knew was the following: for low frequencies, it was 1 by beta approximately, and for high frequencies, it was following my open loop gains transfer function. So now let's look at all the 3 cases. Let's start with, what can I start with? Let's start with critically damped case. So the closed loop poles, what can you say about them? They are exactly on the same location. So if I plot this, it's going to be flat till it hits both the closed loop poles. So here is where, let us say, omega n is there. At this point is where you have both the poles. So at what slope will the magnitude plot drop by? Minus 40 dB per decade. Let me see if I can match this line. No, I can't. Okay. Okay, maybe just to clear, this was what we assumed earlier, right? For low frequency, high frequency, I am just plotting in yellow. This is something we knew already. Right? Okay, next let's look at overdamped case. So if the closed loop system was overdamped, how will the closed loop magnitude plot look like? It's going to start here. I have 2 poles, right? So the lower frequency pole will occur before this or after this? I know lower frequency pole is before omega n. So it's going to start to drop, let's say at somewhere here. And what will be the slope? Minus 20. Okay. And remember that at very high frequencies, I should still be following this line. Okay. So again, if I do a thing, second pole should hopefully lie here. Make sense? Because at very high frequencies, I have to follow this line. That much was already established. Irrespective of what kind of damping I have, low frequency, this should be the behavior. At very high frequencies, this should be the behavior. So that's why I'm roughly plotting it like this. Okay, then let me ask this. So let us say this I have plotted for some zeta of 2, let us say. Now if I increase the damping factor to, let us say, 3 or 4, how will the plot change? Which means the question I have to answer is, if I increase the damping factor, the lower frequency pole, do you think it will keep moving lower or it will start increasing? Why? Why? Yeah, why spread out? It's nice to remember results. That's good. What you told is absolutely right. But can you, if you don't remember it, can you actually make? Yeah, one thing is here you put, I put zeta as 2, you put zeta as 4 and see what happens. But when you have questions like this, think on limiting cases, right? So let us say you put zeta to infinity. What will happen? Let us say this is the thing, zeta is infinity. What will happen to the pole locations? If zeta, let's say zeta is really large. Let's not even take infinity. So what will happen to this expression? Zeta is very large. This will approximately be zeta. So what will happen to the pole locations now? One will be 0. One will be at minus 2 zeta omega. So one is going to a very low frequency. So obviously, the low frequency pole will do this, and high frequency pole will do this. Is okay? In fact, if I keep pushing zeta and tend it closer and closer to infinity, you will find one pole will move to 0, other pole will move to infinity. Okay. So this is hopefully clear. So this plot is for let's say it's zeta 2, and I guess I don't want to mark it. You understand, right? If the zeta increases, the curve does this. Cool. So then we are only left with underdamped case. So if it is underdamped, how will the plot look like? Again, low frequencies, it's fine, it's doing this. What will happen for underdamped case? Correct. Poles will have, the poles are of the form sigma naught plus or minus j omega naught. So how will the frequency response plot look like? Okay, again think of some limiting case. So let us say zeta is very, very small than 1. What can be a limiting case for zeta? 0. Let's take zeta 0. If I put zeta 0 here, what is the transfer function I get? Zeta 0, what is the transfer function? K naught omega n square, right? To plot the Bode plot, what will I replace S with? This is the transfer function. We are looking at sinusoidal frequency response. So we are looking at S equal to j omega. If I do that, what do I get? If I plot this, what will happen at omega n? It will be infinity. Is that okay? So if at omega equal to omega n, the closed loop transfer function goes to infinity. This is for zeta equal to 0. Now if zeta is, let us say, not 0, something smaller than 1, what do you expect? Yeah, it will have some large peaking. That much should be clear. Okay, and that peaking will be equal to this frequency. Whatever we have omega by whatever you have here. Okay. So again, if I do this, I'll have some peaking like this, and then it will nicely fall this. Okay. So this is for underdamped case. Again, now it should be clear that if I reduce zeta, this is going to peak further and further. Right? This is for smaller zeta. Great. Okay, this is in frequency. Again, let's look at the time domain thing, what happens. Let's assume that I am looking at the step response of the closed loop system. Again, this is all in closed loop, remember. And let me tell you that if the system had no poles, the output ideally steps up like, jumps like this. There is no pole, no delay, things respond immediately. This is an ideal output plot. Now let's plot for all the three cases. Let's start with underdamped. If I have an underdamped system, how will the step response look like? Again, if you're not, what? No, tell it's okay, whatever you have. Rising exponentially, okay. So let's look at, again, if you're not remembering, it's fine. We can just take limiting cases and find out, right? I'll take the same limiting case. I'm taking zeta 0. So this, this will be the transfer function for zeta equal to 0. So how will the, if I take the inverse Laplace transform of this, what will be there? It will be some kind of sinusoid. Fine. So what do you expect in the step response? If zeta is 0, it's going to nicely oscillate. But my zeta is not 0. So what will happen to the oscillations? It will kind of decay. So it will do something like this. Make sense? Again, you don't have to remember anything. Just take some limiting case and you should be able to argue. Right? That's how you should learn anything, right? It's not just about remembering things. Remembering things is the main thing computers would have won already. Just because we can still process and make some intuitive sense like this, we are still there. Okay, again, okay. Then what can you say about this envelope? Let us say the closed loop poles are sigma naught plus or minus j omega naught. The oscillation frequency is roughly omega naught. What can you say about this decay? This envelope. Yeah, this will be e power minus sigma naught. And remember, any LTI system, if I have a pole like this, the natural response will be this, right? Again, things are not in left half plane, so I'll have minus this. So I'll have e power minus sigma naught t times e power minus j omega naught t, right? So the decay will be dependent on the real part. Okay, great. So now if I look at critically damped case, how will the response look like? No, it's critically damped. Sorry? See, it will be an exponential. Is that okay? There will be no sinusoidal drinking. Okay. Think of it like this, right? If zeta is 0, it is going to oscillate properly. As zeta increases from 0, the oscillations start to die. And exactly when it is 1, there is nothing happening. Okay, then one last thing, underdamped case. How will it look like for underdamped case? Yeah, exponential, but he is saying this will be longer. Why is that so? Yeah, you think about it like this. For overdamped case, the lowest frequency pole is smaller than that for critically damped case. If the pole location is smaller, the system is faster or slower? Slower. Okay. If there is no pole, the pole is at what location? Infinity. So infinity is infinitely fast system. So if the pole is coming to lower and lower frequencies, it is going to lag more and more. So overdamped will be this, and if I increase zeta, it will become even slower. Okay. Great. This should not be new to you guys. Hopefully you have read it. I am just interpreting the same thing you read in a different way. Okay. Cool. So now I know that I can have 3 different cases for my second order system when I use it in closed loop. Which of the 3 would you prefer? Look at the step response. Ideally, you want to settle faster or slower. So which of the two is, which of the cases is the best? Critically damped. Okay. I mean, it looks like this is faster, but this is unnecessarily ringing. You don't want to overshoot and undershoot and stuff. So critically damped case is usually the best case, and that's what we aim for. Okay. So, and for that, the damping factor should be chosen to be exactly 1. Okay. So now again, remember we all started with seeing what will happen if I have an amplifier and the amplifier has 2 poles, and I am taking the 2-pole amplifier, putting a negative feedback, and I see I can have all these 3 combinations. Now my goal is to make sure that when I put it in negative feedback, I end up with a critical damping case. So we'll have to see how we can design the amplifier's parameters to meet this. Okay, that should be our goal. I know what is the damping factor. So I know this should be equal to 1. Let's see how I can make it 1. I want this to be exactly equal to 1. Right? Now let me assume that I have the 2 poles to be roughly on the same location. When I say P1, P2, these are poles of what system? Open loop system. That is, the amplifier's poles is what we are talking about. Okay. So if, let us say, the amplifier had 2 poles and both of them are roughly equal, how can you approximate? I mean, what will zeta become? 1 by 2 k0 beta. So do you think this will be a small number or a large number? This will be a really small number, right? Because you want a really large A0. So this, I will say, it's approximately 0. So is this a good thing to have or a bad thing to have? It's a bad thing to have. Okay? Because as we saw, if zeta becomes closer and closer to 0, I'll have more and more oscillations. So which means when you design the amplifier, and if the amplifier has 2 poles, how will you choose them to be? They should be far apart. Okay. So I know that I will say for stability, again I am just coining the term stability. By stability I mean if I apply a step input, I don't see sinusoidal ringing at all. So this implies I should have one of the poles to be greater than the other. Is clear? Cool. So let's impose that condition on this equation. I am assuming P2 to be much greater than P1. Can you simplify and tell me what will zeta become? If P2 is okay, if P2 is larger than P1, which of the 2 terms will dominate? First term or second term? Right, so that's all. You just take it. So this is basically 2 root A0 beta times the second term, which is P2 by P1. Yeah, now I know that the expression for zeta is correct. So this is basically 1 by, you can write it like this, 1 by 2 square root of P2 times beta A0. And you want the damping factor to be 1 ideally, that's the target you want. So that should give you this straight away. My P2 should be 4 times beta A0. Okay. So again, equal to 1 is the ideal point you want, but of course in practice you can't get things exactly the same value you want it to be. So if I can go slightly here and there, would you want it to be smaller than 1 or less than 1? Sorry, smaller than 1 or larger than 1? Larger than 1. You don't want to go in this underdamped territory because that has ringing. So ideally this is what I want, but if I can have some choice, I'm okay with this also. right? So I will say for stability you can have something like this, zeta to be greater than 1. So which means my second pole should be at least greater than 4 times the beta A naught P. Okay. Great. So let's just do one thing. So is this point clear? Cool. So now let's actually redraw our plots, right? Because earlier I randomly chose some P1, P2 when I started, right? Now I know that if I need to have something reasonably stable, my second pole should be greater than the first pole. So let's quickly redraw the magnitude plot. So again, let me remind you, loop gain is beta A naught by 1 plus S by P1 times 1 plus S by P2. And I know that to have reasonable stability, my second pole should be greater than the first pole. In particular, to get critical damping, second pole should be 4 times beta naught P. So let me quickly sketch it. So omega, magnitude of the loop gain. So it's starting from beta A naught. So let us say it hits the first pole here, and let us say second pole is somewhere here farther apart. Okay, or yeah, let me first draw this. Let's say second pole is somewhere here. I've made sure that P1, P2 are sufficiently apart. Okay. Again, this is the 0 dB line, and this is the unity loop gain frequency. Okay. So this is my loop gain expression. L of S is, I mean it's there, I don't want to write it again. So this is the loop gain expression. So let's try to compute what this frequency might be. So okay, I mean of course one thing is to put S equal to j omega, take the magnitude, equate it to 1 and get an exact 2-page long equation. But let's do something better. So can you tell me the location of omega U loop with respect to P1, P2? If I choose P1 and P2 to be sufficiently far apart, so can you tell me omega U loop's position with respect to P1? Do you think it will be smaller than P1 or larger than P1? Right? So I know omega U loop is going to be much larger than P1. That much is known. And what can you say about P2? It's going to be smaller than P2. So let's use this condition. So in this expression, I know that I am looking at a frequency greater than P1. So how can I approximate the first term? One plus S by P1. I am looking at a frequency much greater than P1. So how can I approximate this as S by P1? Fine. Look at the second term, 1 plus S by P2. I am looking at a value of frequency much smaller than P2. So how can you approximate this as 1? Okay. So again, now you take the magnitude, equate it to 1. What do you get for omega U loop? Yeah, beta times I mean this shouldn't be surprising because see the way I have chosen the poles are such that when this crosses the unity line, it is still acting like a first order system, right? Because the second pole is occurring much later, right? So when it's crossing the 0 dB line, it has still only encountered one pole. So you can still approximate this to be a first order system till this much. And for a first order system, I already know this was the unity loop gain frequency. No, I don't know. That's we are trying to find omega U loop, right? I mean, this was P2 is 4 times beta A naught P1. This is the condition for zeta to be 1. No, I mean this is something that we saw earlier. Okay. Now I am trying to find omega u loop, and that incidentally turns out to be this. Okay. This and this have no relation. Okay. Now we can make relation. Tell me what is the relation now? P2 is omega loop for zeta equal to 1, and if you want this to be greater than 1, you choose P2 to be greater than that. Okay. So again, let's rewind everything back. So the idea is to have an amplifier which has two poles, and we want to make sure that when that amplifier is put in negative feedback, it is stable. That is, I want it to be either critically damped or over damped. And to see if the closed loop system is over damped or under damped, in principle I have to calculate the closed loop transfer function, right? Find the location of the poles and then see whether it is over damped or under damped. Correct? Now that's obviously it's not straightforward, because as engineers one thing we can all agree upon unanimously is we don't like to solve any equations, right? We want to solve only linear equations, one equation, one unknown, that's all. So solving roots of second order equation and finding where the poles are located, it's not doable. So that is why we do the following. We try to understand if the damping factor is equal to 1 or less than 1 from this plot. And the translation is this, right? If I can have a case where the second pole is greater than my omega u loop, then I know that my zeta is okay. That fine? So this is basically like rephrasing that required information in terms of Bode plot. Okay. So this is the condition. Yeah, correct. That's the condition exactly. To get zeta equal to 1, in principle you should have calculated the closed loop poles, find if they are on the real axis, imaginary axis, how far they are apart. Instead of doing that, I am just plotting the Bode plot and seeing if my second pole is greater than omega u loop. Now how much greater it is compared to omega u loop will define exactly how much is the zeta. Okay. Now of course if you want to know information on location of two frequencies, you can look at the magnitude plot, but you get much more information if I look at the phase plot, because if I take some simple transfer function like this, right, say it's k by 1 plus f by p, I plot the magnitude and phase. So magnitude is going to look like this. This is the magnitude of h, let us say. If I plot the phase of h, it is going to start from 0, reach minus 90. At the pole location, what will be the phase? Minus 45. Okay. So roughly I am drawing. Okay. This is minus 45. See, now look at this, right? If I were to make distinction between these two frequencies, from magnitude plot, I hardly cannot make anything. But if I look at the phase, I can really say how much the frequencies are apart, right? So even if I look at the location of the pole, right? I mean, the Bode approximation does this, but in reality, it will do this, and the drop will be how much? 3 dB. So even at the pole location, the drop in magnitude is only 3 dB, but how much is the phase? 45 dB. Okay. So that's why most of the information you get from the phase plot, because magnitude masks a lot of information. Okay. So our goal is to see how much my second pole is with respect to the unity loop gain frequency, and for assessing that, instead of looking at the magnitude plot, we will look at the phase plot. That's the idea. Okay. So for the same thing, I'll quickly sketch the phase plot. And if I quickly sketch the phase will start from 0 and reach what value? Minus 180. So I'll roughly draw this. Okay. Something like this. Okay. So now tell me, my goal is to find how far my second pole is with respect to omega u loop, right? So which means I look at the phase at this frequency, okay? and my goal is to see how much it is away from the second pole. Now I know if I have two poles in the system, what value the phase will reach to? Minus 180, right? So I'll basically try to find how much is it away from minus 1. And you guys know what this is called? What is this called? Okay, phase margin, if I say, it should ring a bell. Okay, it's not alien. And that's why we look at the phase margin. Okay. So again, I just introduced it in a slightly hand-wavy way without going to a lot of technicalities, but I think this should make the point. So to paraphrase it, I am interested to see if my closed loop system is critically damped or over damped. For that, in principle, I should look at the location of the closed loop poles, but instead I am trying to map into this condition that my second pole should be farther than omega u loop, okay, and that I am checking using phase margin as a proxy. So now you tell me if my zeta increases, do you think the second pole will move farther away from omega u loop, or it will move closer? It is going to move farther away, okay, because the condition is this, remember, P2 should be greater than this for larger zeta. So if the zeta increases, what can you say about the phase margin? Decrease or increase? Okay, think about it. I have some zeta. If I keep reducing zeta, the system is more stable or less stable? Less stable. So which means if I keep reducing zeta, the phase margin should increase or decrease? Decrease. Is that okay? So if my system is more and more stable, the phase margin is also going to be higher and higher. Think about it like this, my second pole is moving farther and farther. So which means the phase will drop after a long time, right? It will do this and do this. Right? Maybe this phase plot is not explaining clearly. So let us say I have something like this. Okay. If my second pole moves farther, this will reach 90 and then do this, right? Because if I assume second pole is somewhere here, then I will find that the phase margin is going to be higher. Okay. Cool. So one last thing, again, I remember the ideal point I want is zeta equal to 1. So now I have to map this zeta to phase margin, right? Because I am using phase margin as a proxy to determine if my system is over damped, under damped and stuff. For that, let's quickly find out the phase margin. So to find the phase margin, I will need to first find what is the phase at omega u loop. Okay. So let me take the transfer function. So if this is the loop gains expression, tell me what is the phase of the loop gain at some frequency omega. This is the transfer function. What is the phase at a frequency omega? At any frequency omega, if I were to write the phase, what will that be? Minus tan inverse omega by P1, great, omega by P2, okay, fine. Now I am interested to find the phase at what frequency? Omega u loop, okay, this is because I am interested to see how much the phase at omega u loop is away from minus 180. So at, let us say, omega equal to omega u loop, if I try to find the phase, I know P1 is much smaller than omega u loop. So I have tan inverse of omega u loop by P1. So it is tan inverse of a really large number. Tan inverse of a really large number is what? 90. Okay. Is that okay? The other way to see is the first pole has come at a much lower frequency. That phase has already reached minus 90 when I hit omega u. And what about the phase due to the second term? I mean, let's not make it 0, it's tan inverse of omega u loop. So this is the phase. Now to find the phase margin, I will take this phase, subtract it from minus 180. Okay. If I do that, this is minus 180, remember. What do I get? I'll just write it, it's 90 minus this is what I should do. I mean, this kind of calculation, is it the first time anyone seeing, or you have seen this before? You have seen this before, right? So hopefully this is just some kind of a recap. So let me write the phase margin expression separately. This is what we have. So let me just make some final remarks. Now again, remember my goal is to keep zeta to be 1. Now the condition for zeta to be 1 is second pole is 4 times beta a naught p1, and I found that beta a naught p1 is approximately omega u loop. So which means what is the corresponding phase margin? I have 90 minus what number? 1 by 4, or can you see carefully? Oh, sorry, 1 by 4, sorry, you're right, yeah, 1 by 4. Oh. And tan inverse of 1 by 4 is roughly 14 degrees. So this is basically 76 degrees. It's nice thing to remember, right? 1 by 4 is 14. Not that difficult. Okay, so that's the bottom line. My final goal is to make sure that when I have a 2-pole system, that is an amplifier which has 2 poles, and I put it in negative feedback, that closed loop system must have critical damping. Now to ensure if that is going to happen or not, I will just look at the phase margin of the loop gain and then see if it is 76 degrees. That's the end of story. You don't have to find the closed loop transfer function, look at the poles and see where they are located. Okay. And just a couple of minor points before we leave. So till this point, any questions? Hopefully things are okay. Just take your time to process and let me know if you have doubts. Yeah, so one point to notice, where did we calculate? Yeah, see here I calculated that omega u loop is beta a naught p1, and in this calculation the assumption I made is this. Okay, these two. I mean, this first condition will always be satisfied. Typically, you know, like you'll have the first pole somewhere here, it will be fine. The second condition is what is critical. Okay. So the expression we calculated is correct if my second pole is sufficiently greater than omega u loop. Okay. If it is not, then this expression is not correct. Okay. And in fact, I'll give you a problem you work out. We'll see in the next class maybe. So let me give a condition. Let me give a case wherein again it's a second order system. Same thing. Okay. Yeah, I find that the phase margin for the loop gain is 45 degrees. So for this case, calculate omega u loop exactly in terms of beta a naught and p1. Then you will understand what I am talking about. So take this as a problem to work out. We will discuss it in the next class so that you get used to this. Cool. So I'll stop here and we'll